So now I want to consider an example where we are starting from a problem consisting of a description in words and turn it into a mathematical problem of equations and constraints. So we're taking the example of the nutritionist from the notes. It's example 3. I'll have a copy of the problem in the description. And so first we want to find the variables. These are the things we can control, the things that can be adjusted, something we want to find the quantity of. And then in terms of those, we find the objective function, and that is something we want to minimize or maximize, and then we'll figure out the constraints. So looking at the problem, if we look down to the last sentence, it's asking how many grams of each food should be used to minimize the cost of the meal. So the amount of grams of each of the foods is something that we can adjust up or down. So the variables are going to be how many grams of each food. So it's the grams of each food, which is going to be the variables. So there are two foods, A and B, so we're going to say let XA be the number of grams food A, XB be the number of grams of food B. So these are our variables, and our objective function will be a function of these variables. And if we continue the last sentence, how many grams of each food? 2 is to minimize the cost. So the cost is going to be our objective function. So we have to calculate what the cost is. So cost is going to be a function of the number of grams of food A and the number of grams of food B. So it's a function of XA and XB. And each gram of A costs 2 cents. So if we have X grams of A, it's going to contribute 2 times XA cents to the total cost. And each gram of B, XB, will contribute 3 cents. So the cost is going to be this, and we say it is in cents. So these are our variables, this is our objective function, and now the tricky part, or slightly slower part if you like, is to figure out what the constraints are. So 3, the constraints. If we look through the problem, we find that the nutritionist wants the meal to provide at least 360 grams of units of protein. So that's one constraint, because it's at least, it's going to be greater than or equal to 360. So units of protein has to be bigger than 360. And the units of protein will be a function of how many grams of each food, but we can figure that out next. And likewise, we want units of iron has to be at least 270, and units of thiamine has to be at least 450. And so we can if we figure out what the units of protein, iron and thiamine are in terms of how many grams of each food, then we'll have our constraints, as well as possible non-negativity constraints. Okay, so if we want to calculate the number of units of protein, we see from the problem description is that each gram of food A contains 60 units of protein. So each gram of food A will contribute 60 units of protein, and each gram of food B will contribute 30 units of protein. So 30. So units of protein is going to be $60xa plus 30xb. And likewise, units of iron, food A, 1 gram of food A contributes 30 units of iron. So food A will contribute 30xa units of iron, and food B contains 30 units of iron per gram as well. And food A contains 30 units of thiamine per gram. So 30 times the number of grams will give us how many units of thiamine for food A, and 90 units of thiamine per gram of food B. And so we have from these here, it should be greater than 360, that should be greater than 270, and that should be greater than or equal to 450. And likewise we need XA and XB to be non-negative, because we're measuring grams of food. To express the problem in a purely mathematical form, we can say we want to minimize the function cxaxb, which is 2xa plus 3xb, subject to the constraints as follows here. So in this form we're just talking purely about, here's a function of two variables and we have some constraints, and we can solve this graphically. We can draw a feasible region and we can find the vertices, and then we evaluate the function at each vertex and see where the function is minimized. Okay, that's all.